Unit 5, Current and Resistance. Lesson number 5.3, Resistance and Resistivity, Part 2. Learning objectives. To calculate resistance of resistor by reading the color code. To use the temperature coefficient of resistivity to solve problems involving changing temperature. To explain microscopic basis of conduction in solids. Keywords: resistor color codes and temperature coefficient of electric resistivity. Resistor color codes. The colored rings were used to define the amount of resistance because the resistors were small in order to reduce the costs of production and sale. There are rings on these resistors coated with several different color bands, each of which indicates one of the resistance values, and the sum of them gives the amount of the resistance. Resistors are color-coded with marks or bands that allow you to quickly identify values and tolerance. Using a color chart table will allow you to determine of any common four bands. Memorizing this color chart will enable you to become proficient in quickly decoding and using resistors. In a four-band resistors, the first two bands represented digits or significant figures. The third band indicates the multiplier, and the fourth band indicates the tolerance. You read the resistor bands beginning with the end that has the most bands. A space between the third and fourth band also indicates the reading direction. Example 1. The first band is red, so the first digit value is 2. The second band is violet, so second digit is 7. The third band is yellow, so we multiply the first two numbers by 10 power 4. Thus, the value of this resistor is 27 times 10 power 4 ohm, equal 270 kilo ohms, with a tolerance of plus or minus 5%. In this example, the first band is orange, so the first digit is 3. The second band is white, so digit 2 is 9. The third band is silver, so we multiply the first two numbers with 10 to the negative 2 power, or 0.01. In this instance, we would take the 39 and move the decimal point 2 places to the left, resulting the value 0.39 ohms. Thus, the value of this resistor is 0.39 ohms, with a tolerance plus or minus 10%. Now, let's determine what is the bands would be on 15 kilo ohms resistor. Since the first digit is 1, the first band would need to be brown. The second digit is 5, so the band color would need to be green. The resistor value is 15 kilo ohm, so we need to add 3 zeros to 15. 3 zeros is 1,000, so we need to have multiplier of 10 power 3. Thus, the third band color would need to be orange, and last band would need to be silver to indicate that the resistor has a tolerance of plus or minus 10%. Temperature dependence and superconductivity. Values of resistivity and resistance vary with temperature. For metals, this dependence on temperature is linear over a broad range of temperatures. For the conductor, higher temperature, that means higher resistance. For metals and a lot of insulators, when temperature is raised, the lattice ions vibrate more vigorously, increasing the frequency of collision between electrons and the lattice. The average drift velocity is reduced and the resistance therefore increases. an empirical relationship for the temperature dependence of the resistivity of a metal is rho minus rho null equal rho null alpha times T minus T null, where rho is the resistivity at T temperature and rho null is the resistivity at temperature T null. Alpha is the temperature coefficient of electric resistivity. Is defined as the measure of change in electrical resistance of any substance per degree of temperature change. Alpha is measured in units Kelvin to power minus 1. Thus, the temperature dependence of the resistance of a conductor can be approximated as R minus R naught equal R naught alpha times T minus T naught, where R is the resistance at T temperature and R naught is the resistance at temperature T naught, and alpha is the temperature coefficient of electric resistivity. Note that equations 1 and 2 deal with temperature differences, so the temperature can be expressed in degrees Celsius or Kelvins, but not in degrees Fahrenheit. Below a certain critical temperature, resistance becomes zero, allowing current to exit without energy wasted. Superconductivity, although predicted and discovered a century ago, has only become useful recently due to the development of rare earth conductive ceramics. Superconductive wires are used in electromagnets of MRI machines. Magnets constructed with superconductors use less power and can produce higher magnetic fields than magnets constructed with conventional resistive conductors. Copper is the most widely used material because it is quite malleable, ductile, and available. Aluminum was tried for general wiring, but because of its thermal characteristics created difficulties. Silver and gold are used, but because of cost, they have been limited to places that justify the cost. Tungsten have a resistivity 3 times that of copper, but there are occasions when its physical characteristics, durability and hardness are the overriding considerations. For semiconductors, when temperature is raised, greater vibration of atoms takes bonds, freeing more charge carriers, such as electrons, and therapy producing a marked decrease of resistance. Then, in semiconductors, increasing temperature causes decreasing for electric resistance. As in figure 5.9, the temperature dependence of the resistance of the thermistor. Exercise 1. The following diagram represents the relationship between the electric resistance of a metal wire and its Celsius temperature. Consider that the starting temperature is 0. What is the relationship between the electrical resistance of the wire and its Celsius temperature? From the figure, the resistance is directly proportional to the temperature. What is the electrical resistance of the wire at 0 degrees Celsius? From the figure, the resistance are equal 0.5 ohm at 0 degrees Celsius. How much is the temperature coefficient of the specific resistance of nickel chrome? From equation 2, alpha equal R minus R null divided by R null times T minus T null equal 1.5 minus 0.5 over 0.5 times AT minus 0 equal 2.5 times 10 power minus 2 Kelvin to power minus 1. Exercise 2. Choose the right answer. Alpha is coefficient of resistance A. Temperature, B. Voltage, C. Current, or D. All of the above. The right answer is temperature. Exercise 3. The diagram shows the relationship between the resistivity of copper with temperature. If you know the chamber temperature T null equal 293 Kelvin and its specific resistance was rho null equal 1.69 times 10 power minus 8 ohms meter. Calculate coefficient temperature alpha when its temperature reaches T equal 1200 Kelvin. From equation 1, alpha equal 1 over rho null delta rho over delta T. And from the figure, alpha equal 1 divided by 1.5 times 10 power minus 8 times 8 minus 1.69 times 10 power minus 8 divided by 1200 minus 293 equal 4.8 times 10 power minus 3 Kelvin power minus 1. Exercise 2. A tungsten filament bulb needs 374.3 milliampere of current when it uses a voltage 3.907 volt. When the lamp is at room temperature of 20 degrees Celsius and is not lit, the resistance of its filament is 1.374 ohms. If you know that alpha for tungsten equal 4.50 times 10 power minus 3 Kelvin minus 1. What is the temperature of the tungsten filament when it is lit? From equation 2, R minus R null equal R null alpha times T minus T null. And from Ohm's law, R equal delta V divided by I. So delta V divided by I minus R null equal R null alpha times T minus T null. So T equal delta V divided by I minus R null divided by R null alpha plus T null. And by compensation on the last equation, T equal 3.907 divided by 0.3743 minus 1.374 divided by 1.374 times 4.5 times 10 power minus 3 plus 20. So T equal 1520 degrees Celsius. Exercise 3. Choose the right answer. If the temperature of a copper wire of resistance 100 ohm increased by 25 Kelvin, what is the change to the resistance? If you know that alpha for copper equal 3.9 times 10 power minus 3 Kelvin power minus 1. A will increase by 10 ohms. B will increase by 4 ohms. C will decrease by 4 ohms. Or D will decrease by 10 ohms. From equation 2, R minus R null equal R null alpha times T minus T null. Then delta R equal 100 times 3.9 times 10 power minus 3 times 25. Delta R equal approximately 10 ohm. So the right answer is A will increase by 10 ohms. Microscopic basis of conduction in solids. Conduction of current through solids results from the motion of outer electrons drift in the direction opposite to that of the electric field. The outer electrons of each atom are essentially free to move randomly in this lattice. Resistance to drift occurs when electrons interact with the metal atoms in the lattice. When the temperature of the metal is increased, increasing the resistance of the metal. Why this happens? Because the motion of the atom in the lattice increases. This in turn increases the probability that electrons interact with the atoms, effectively increasing the resistance of the metal. Atoms of a semiconductor are also arranged in a crystal lattice. However, the outermost electrons of the atoms of the semiconductor are not free to move about within the lattice. Semiconductor has a higher resistance than a metal conductor. Can you explain why? Because to move electrons inside semiconductor must be given enough energy to attain an energy state where they can move freely. So, it has many fewer conduction electrons and higher resistance than metal. The resistance of semiconductor goes down as its temperature increases. Can you explain why? Because When a semiconductor is heated, many more electrons gain enough energy to move freely, and then the resistance goes down. Let's summarize. The value of the resistance is indicated by 3 or 4 color bands on plastic covering. The first two bands indicate numbers for the mantissa. The third represents a power of 10, and the fourth indicates a tolerance for the range of values. The temperature dependence of the resistivity of a material is given by ρ minus ρ null equal ρ null alpha times T minus T null, where ρ is the final resistivity, ρ null is the initial resistivity, alpha is the temperature coefficient of electric resistivity, T is the final temperature, and T null is the initial temperature. Thank you all and have a nice time.